Hello everyone. I'm Christian Chown. I'm a React and React Native contractor. My most recent contract was with the bank Santander, where we were developing a greenfield React Native app. I'm not by any means a security expert, but developing an app for a bank has its own set of security challenges, and some of those learnings I'm going to talk about today. I'm going to talk about using JavaScript obfuscation to secure your codebase, and certificate pinning to secure your API calls, and finally, jailbreak detection to secure your data. So, using JavaScript obfuscation to secure your codebase. We're React Native developers. We create IPA files for the App Store and APK files for the Play Store. There's no such thing as an IPA file format. These are just zip files. You know, if you change the extension on them, run them through your zipper, you can see what's inside them. This is one of my IPA files and a bunch of icons, some assets, and next to my info plist is my main.js bundle. Similarly, here's an APK file, a bit of a flatter folder structure, but there in the assets, next to my fonts is my Android bundle, index Android .bundle. But does that matter? What can you actually see if you look transpiled, minified code? I mean, it's quite condensed anyway. So, as a proof of concept, I spun up a Create React app. This is it here. So, hang on, let's see if I can spin to that. There is my Create React app. And in it, I put a sensitive piece of information, in this case, a secret key. And here's that same app, transpiled and minified. You know, it's fairly condensed, but the strings are fairly visible in there. And in fact, if I look at this middle section here and then run it through Prettier, you can see that this is that app component that you just saw. It's really nice, clean, clear ES5 code. So that's, you know, a testament to the clean abstraction that underlies React. However, it's very easy to reverse engineer this. And just to show that's not specific to Create React app, this is from one of my live production APK files. This is a part of my login form. It's the same nice, clean, clear ES5 code, but instead of DOM elements, there's React Native views, React Native styles. And in the center of my bundle, here's the credentials for my Firebase database. Now, these are client-side credentials, yes, but it's not something I'd necessarily want completely so open and visible. You know, so how hard would it be for someone here, say, I think quite a lot of this room could do this, write something that extract all the strings from a JavaScript file. In fact, you don't even need to write it. There's an NPM module for that. And in fact, how difficult would it be to write something that unzipped APKs and IPAs? You know, if you give it an APK file, an IPA file, and it will extract some React Native JavaScript. How difficult would it be as well to scrape a website and download any APKs or IPAs you might find there? What have you got? You've just written a tool that will extract from the App Store and the Play Store every single React Native app, every string, and then put it into a spreadsheet for you. Who knows what treasures you might find in there? So, going back to our original bundle, I took this and I gave it to the bank's penetration testing team. And I said, can you find the secret key? And they went, yes, there. So then I ran it through a commercial JavaScript obfuscator. Would you like to see some commercially obfuscated JavaScript? Of course you would. Yes, yes. It looks like this, and this, and this. Pages and pages and pages of utterly impenetrable garbage. This is my preview pane on VS Code. You can get the idea there. I showed this to the pen test team and they went, what am I looking at exactly? So, yeah, this is commercial obfuscation. I've run similar bundles through the open source JavaScript obfuscators. They do a good job too as well. And all of them just run off a single line shell script. You know, you give it an input file, an output file, a few config settings, and you get an obfuscated version of the same JavaScript. And while it's use case dependent, you might think, well, this is actually of some value to me. So how would you incorporate that into your React Native build process? One option would be to do it during transpilation. There's a NPM module here, which is React Native Obfuscating Transformer. If you've ever added TypeScript to a React code base, it's the same idea. It's a Babel transform, and that will then obfuscate on a file-by-file basis. We chose a different approach. We chose to do it during the bundle phase when we had the entire JavaScript bundle to work on. There were two main advantages to this. Transpiling the entire bundle gives the obfuscator a bit more scope to move stuff around. And because we didn't have to provide interoperability between the files, it meant that every single identifier name could get mangled, which allowed us to produce the kind of results that we did there. And how would you actually do that? Right, well, here is your favorite app and mine, Xcode. We're in the build phases tab of this target. The final build phase here is bundle React Native code and images, which looks like this. It just runs a shell script within the React Native node modules. And this is where we chose to obfuscate. Not much of a change. It's basically sniff out the release configuration, say that we're doing it, run the same shell script we were before, and then run the obfuscator on it. And Xcode will then just take all that obfuscated bundle and just apply that into our final IPA. Android, a little bit more involved. This is my app level build.gradle. Final step here, again, is something off the React Native node modules. We add an additional obfuscate step. This is the skeleton of the obfuscation script. One thing, if you ever write any Gradle scripting, Gradle is written in the Groovy language, which is very, very similar to Java in appearance. However, I got caught out because Groovy is declarative, not imperative. So you kind of declare individual tasks and then you link them together through a dependency chain. The final step is normally this assembly step, which normally depends on the packaging step. So it packages up your APK and then assembles it. So what we did, we just stuck 3 tasks in the middle. The first one, we said, okay, that thing you've packaged up, I want to unzip it. I then want to obfuscate the bundle, and then I want to rezip it. This is what the tasks look like. I can't claim any ownership for this code, by the way. This is all completely cannibalized from an example app. But just to give you some idea of, this is the real thing. This is what it's doing. We basically say this one's a copy task. So from my zip, I want you to grab the index Android bundle. The input is my APK. My output, I'm going to stick in my temp file, the Android bundle. Then I'm going to run the obfuscation shell script, single liner, same as we did for iOS. Input, output, and the arguments all the same. So then obfuscate in place my Android bundle, and then reassemble the APK. So the input is my obfuscated bundle, my output is my APK. This first bit says, get everything from the original APK, but exclude the Android bundle. But from the temporary directory, include that Android bundle. And that's it. We've obfuscated JavaScript in our app. And what we do, we're now protected against a fairly unsophisticated attacker. It doesn't take a very great deal of skill or effort to subject JavaScript to static analysis. And while there is some setup cost, it's a one-off cost. You can add this to project after project in a matter of minutes. There are some trade-offs. First off, if you're using anything like Crashlytics, you're not going to get the nice stack traces you were because of all the control flow flattening and all the other mangling that the obfuscate's going to do to it. Normally, most of the obfuscators do give you a source map, but it's an extra step, bit of a hassle. And finally, your bundle is going to be bigger, and as a result, it's probably going to be slower. For our case, in the bank, we were doing a banking app, not too much heavy lifting on the JavaScript side. And we found it didn't hurt, really. There was no noticeable difference. But generally, I've found if you're having performance problems in React Native, is it because you're doing too much work on the JavaScript thread? Or is it because there's too much going over the native bridge? Spoiler alert, it's the bridge. So, with JavaScript obfuscation, we're now going to talk about certificate pinning to secure API calls. It's hard to think of any app, of any complexity that doesn't need to make API calls. And React Native defaults us to using HTTPS only. It's a good thing. HTTP traffic is clear text. So you can override your React Native app to use HTTP traffic, but it's a hassle, and Apple will ask you to justify it when you try to publish to the App Store, and that's never fun. Plus, we're operating in a hostile environment. What do I mean? Quick primer on HTTPS. When our device opens a connection to yourbank.com, your bank responds with an SSL certificate. And your device will then compare that SSL certificate to the root certificates that it has baked into the operating system. The baked-in root certificates are the ones from the trusted SSL certificate authorities. And the way we link any certificate from, one from your bank to the root certificates is that each of the certificate has a signature and a key. And cryptographically, if you've got a signature and a public key, you can verify and run a little mathematical operation to verify that the signature was created by the private key that corresponds to the public key. And in that way, each certificate can be linked. So now your certificate comes in, you've got the signature of the certificate, it has a link through to any number of intermediate certificates. You compare the signature on that to the public key on that, verify that, intermediate certificate, until finally you reach a self-signed root certificate, and then you compare the hash of that with the hash of the ones baked into your device, and if they match, then you accept that this certificate is valid and you've established the HTTPS chain of trust. So, how might you break the HTTPS chain of trust? Okay, so hi, this is your bank. We've detected a security problem with your Android device. Yeah, if you could just go to yourbank.evil.com, they're just our security partners. Yes, click that link. Yep, security message, perfectly normal. Leave the box checked that says this install only though, because you can't be too careful. Right, now your device will restart and you're completely secured. So I've now installed a web proxy to divert network traffic and a new root certificate. So now any network request to yourbank.com is going to go to a server under my control. I'm going to respond with a certificate that is now signed by the newly installed root certificate. Your app will now accept that as valid. So now every request can be read and every response can be altered, So I'd like to log in with my password. Here's some login credentials, whatever. Transfer £10 to Alex. Transfer £10,000 to Evil Corp. This is now a man-in-the-middle attack. And note that the device has been completely compromised and not one byte of code on the banking app has changed. This is what we mean by we're saying we're operating in a hostile environment, because you can't necessarily trust HTTPS on its own. So how do you protect against that? It's actually quite simple in theory. The idea is that during development, you know the real bank, and so you know the real certificate. And so now, just the same way that you bake a root certificate into your device operating system, you bake the real certificate into your app, or you pin the certificate to your app. And so now, any network request that goes out, you just compare the real certificate to the pin certificate. If it's good, HTTPS connection. If the certificate doesn't match the pin, you just don't allow any network traffic through. And all you do is you'll just receive a 400 error, just like you couldn't open a secure connection. So no compromised data ever gets into your app. Now, is it worth doing this at all? This is the quote from the Open Web Security Project. They say you should pin anytime you want to be relatively certain of the remote host's identity or when you're operating in a hostile environment. Since one or both are almost always true, you should probably pin all the time. They would say that they're a security organization. But if it's not very much effort, why not? There's a couple of decent React Native open source certificate pinning libraries. There's React Native SSL pinning, React Native cert pinning. This is Max Toivonen React Native SSL pinning. He gives you an OpenSSH command. You just give it your URL. He'll then convert the certificate to a CER. You just add those as assets, just like you would a font, a custom font into your app. He provides a swap out for fetch, and you just use that. And that's it, you're pinned. Under the hood, there's a couple of native modules that uses AF networking, which uses the CR and assets, and OK HTTP3, which uses the SSL pinning. Alternative is approves React Native cert pinner. Here, he doesn't provide you a tool for getting them, but there's a couple of online tools you can use to get the base 64 SHA hashes of either the public key or the certificates. And he provides a utility which you put those into a JSON file, and it then generates an info plist or a Java file, which will then get linked in from the native side. Uses TrustKit under the hood for iOS and OK HTTP3 again on Android. If I was going to recommend one of the libraries at the moment, I'd say use approves one. This is because it allows you to pin against the public key. And the reason I'd say do that is if you've ever had a web client who's had their SSL certificate expire, they tend to get very, very cross if their HTTPS traffic stops working. Try and do that if you've got 20,000 apps out there in the wild which are now bricked because of the networking, because the pin will expire when the certificate expires. So the other library, the Max Teuberman library, it has an open issue for pinning against public keys. I'm sure that's coming. And there's a couple of things I quite like about the Max Teuberman implementation, which is part of the pin set is on the JavaScript side, which means it will get protected if you obfuscate your JavaScript. So, certificate pinning. This time we're guarding against a sophisticated and determined attacker. So you might think, could be overkill for your app. But you know what? It's not actually very difficult to do, you know? Once you've set up certificate pinning, you can have it up and running on your next app and your next app and your next app, you know, in a matter of minutes. You know, we like one-off costs. But, like I say, pin against the public key, not against the certificates, else you might brick your app. So, almost there. Jailbreak detection. Now, every one of our apps has access to a sandboxed area slice of the file system, and to our own preferences, and to our own little bit of the keychain, by default anyway. But once your device is jailbroken or rooted, that's no longer true. A rooted user has access to the entire file system. They can access the keychain and Android shared preference of any app. They can install software and they can run executables. And they can operate on modified firmware with who knows what on it. And finally, they could hook into a running app and effectively run a debugger while you're running. It's basically everything other than the iOS Secure Enclave or the Android Trusted Execution environment is available. All that handles is cryptography and your biometrics, but everything else is available to a rooted user. Detecting root access is actually pretty well known and simple. What you just do is you look for files that shouldn't be there, like cydia.app, or you look for folders that exist that shouldn't, but mostly you look for exceptions not to be thrown when you're doing something you shouldn't be able to, you know. Sudo root, what, and you don't complain, you know, so there's that there. And again, there's a couple of open source and React Native jailbreak libraries available. React Native is device rooted and Jailmonkey. First one is React Native is device rooted by Beast. It doesn't look to be under active development, sadly, but nice clean API, just a couple of promisified, get me the device rooted or get me the device locked. But more comprehensive is Gapman's Jailmonkey, which is under active development. Unfortunately, the main maintainer doesn't have the devices, so the PRs are just subject to community testing. And there's methods. These are synchronous, so they only will work on the first fire up of your app. So we've got ones for is jailbroken, whether I'm running on the debugger, hook detection, or external storage. This is quite an interesting one. Detect whether your users can mock location. If you're running an app with sensitive location data, where that's specific, it might be worthwhile for safeguarding reasons to flag that up to other users on their map that you can't necessarily trust that this person's location might be being misreported. So once you've detected a jailbreak, you need to decide what actions you're going to take. Now that will vary according to the needs of each individual app. You might want to just create an access denied page. Just say, nope, sorry, we're not going to run on a rooted or jailbroken device, and then exit. This is what you probably want to do if your app deals with particularly sensitive details or operations which are subject to privacy, like a banking app. Or you might just provide them a subset of functionality. Just say, okay, you can see the balances, but you can't make any transfers because we can't particularly trust that your device doesn't have keyloggers and the like. Or you might just want to flag it up. Or flag it up for other users as well. Just saying that we have this information. It may not be 100% trustworthy. Your mileage may vary. So, root detection allows you to control the access of your app of a user with extended privileges. But unlike the others, which are one-off costs, this will probably need to vary on an app-by-app basis. Plus, there are new exploits being found out every day, which enables you access to the root user. And you'll probably need these devices with these exploits on them in order to test this. Now, when I was putting these slides together, I did a Google search for React Native jailbreak detection. So, number one was JailMonkey, which I've just talked about. And here's Beast's React Native is device rooted. But the third hit I got was bypassing jailbreak detection on a React Native framework. I thought, I better read that. What's the URL? scriptkiddy.wordpress.com. Well, let's have a look at that then. So here's scriptkiddy.wordpress.com. He wrote a little blog article. He was using some iOS fintech app. And he said, while looking at such and such iOS mobile app, I was quite surprised, in a good way, that it had jailbreak detection implemented. So he was surprised in a good way and immediately set about bypassing it. The usual way of bypassing jailbreak detection: first identify the implementation of it, usually by dumping the class and method names and searching for relevant naming conventions. In other words, he's already got tools to statically analyze an Objective-C or a Swift code base, but they don't work with ours because it's React Native. So the main application code he discovers in a React Native iOS application is located in the main.js bundle, and by searching for relevant jailbreak detection methods, we can quickly identify a few related terms. So he beautified the JS code. He ran it through prettier. It's not quite as good as prettier, and he spotted the main return value. I don't know if you can see this, but i.nativemodules.jailmonkey. It's jailmonkey, and he finds the value of the jailbreak detection on around line 82. We simply add an exclamation mark to the return value of is jailbroken call, copy over the edited main.js bundle back to the application on our jailbroken iOS device, rerun the application, done. We've successfully bypassed jailbreak detection with a single exclamation mark. If only there was some way we could have defended against that. And that's when it struck me that app security is more than the sum of its parts. With each bit of security you add to your app, they don't just protect against that immediate attack vector. They also serve as protections for each other. So the JavaScript obfuscation guards the jailbreak detection, which guards against the certificate attack. And while I've talked a lot about hiding and obfuscating and mangling, we're not doing these things for us or our product owners. We're doing it for our users. And it's a great show of faith in us when someone installs our app and uses it. And I can't think of any better way to reward that faith than to secure their privacy. So that's got to be worth one sprint, hasn't it? Okay, that's kind of all from me today. So thank you very much for listening.